Okay, today we're back to finishing up our first set of lecture notes with chapter 18, and then we're going to move on to the ideal gases. And so yesterday we made it all the way up through the first part of thermal expansion, and so we'll finish up these with the thermal expansion topic. Where are we? So right now we're still dealing with one dimension, which primarily is solids, because liquids expand readily in all three dimensions. And so what we covered yesterday was if you change the temperature of some object, in this case a rod, by an amount delta T, the length of the rod will change. In almost all cases, when something warms up, it expands, and when something cools down, it contracts. So in other words, warming up means a positive temperature change, delta T, will nearly always lead to a positive change, delta L, in length. And cooling something down means changing its temperature in a negative way, so negative delta T will lead to a negative delta L, which means objects contract when they cool, and they expand when they're warm. And the amount of expansion or contraction for a given temperature change depends on the initial size of the object, L0, and it also depends on the material, and the effect is characterized by its linear expansion coefficient, which is the fractional change in the length for every 1 degree Celsius change in the temperature. And we see that objects such as aluminum and brass tend to expand more than concrete and steel, and then special materials called Invar expand even less. So we're all familiar with this. Doors expand sometimes when they're heated, and they contract when they're cooled. So we haven't dealt with liquids yet. With liquids, we need to deal with expansion in all three dimensions. And so there's a very similar equation which governs the change in volume to the one that we used before for solids for a change in length. And so for a given change in temperature, delta T, the change in the volume is related to the change in the temperature, the initial volume, and this similar constant here, beta, which is the volume expansion coefficient. And instead of the fractional change in length, it's the fractional change in volume for every 1 degree change, Celsius change in temperature. So with liquids and with gases, we typically deal with this beta because they expand in all three dimensions. And it works for solids too. So let's do an example here. Suppose in the morning you fill your gas tank up with gas, and then the temperature during the course of the day, let's suppose it rises by 15 degrees Celsius or 27 degrees Fahrenheit. And so we know the volume expansion coefficient for gas, and so the question is, if you fill your tank in the morning, how much is the gas going to expand? What's the fractional increase in the volume of the gasoline from morning to afternoon? Okay. So again, here we're using this formula. So if we're trying to calculate the fractional change, it would be delta V over V0, so we divide both sides by V0. And here we're given beta, the expansion coefficient for volume, and we're given delta T. And so we have everything that we need to calculate the fractional change in the volume. So for gasoline, we plug in 950 times 10 to the negative 6, which is 9.5 times 10 to the negative 4. That's the fractional change per degree Celsius. And then we multiply it by the change in temperature, and you see the Celsius units cancel. And we see that the fractional change in the volume of gasoline is 1.4 times 10 to the negative 2, which is 1.4%. So what this means is that over the course of this day, where the temperature increased by 15 degrees Celsius, the gasoline in your tank will expand, the volume will increase by about 1.4%. And so you can, in the morning, if you're going to fill the tank up, leave about 1.5% empty, so only fill it up till about 0.25 gallons out of a 20-gallon tank. Don't top it off, leave about 1/4 of a gallon for the gas to expand, and you won't lose any during the course of the day. So what this says is that you get about almost a 1.5% increase in the volume of that your gas in the tank occupies over the course of the day. So here you can dazzle your friends at the bar with your physics knowledge by telling them to only fill it up to 98.6% of the capacity in the morning, because it's going to expand a little bit anyway. So this isn't entirely true. What we neglected is the fact that the tank will also expand a little bit when it's heated, but it only expands by a small amount compared to the gasoline, and so we neglected the expansion of the tank. Your knowledge of physics just saved you about 60 cents on your next tank fill in the morning, about 1/4 of a gallon on a 20-gallon tank at about $2.40 a gallon will save you 60 cents. So anyway, that's just a simple example of applying volume expansion to gasoline. Now, we've said that all objects, or almost all objects, expand when heated and they contract when cooled. There are a few exceptions. One important one is water. So let's look at this. This is the density of water, and this is temperature. And this is fresh water. And we see that water is most dense at about 4 degrees Celsius. And as we increase the temperature of the water beyond 4 degrees Celsius, the density decreases, as most substances do. They become less dense when heated because they expand. The volume gets greater, and so for a given mass, the density will decrease. If you have the same amount of mass and a larger volume, the density, which is mass per volume, will go down. And so water behaves like most substances as the temperature gets higher than 4 degrees. However, water is a little bit strange, because if you cool the water to a temperature below 4 degrees Celsius, which is about 39 degrees Fahrenheit, water actually expands when it cools too. And usually things expand when they cool, but at low temperatures near freezing, the water actually occupies a larger volume. It expands as it's cooled. And so this has some interesting consequences. So ice is about 10% less dense than liquid water. And that's one reason why ice cubes will float on top of liquid water. They're less dense. So it's also a reason why lakes and rivers often don't freeze over. And that's just because the ice expands as it cools. One bad effect is it also leads to bursting of pipes, water supply pipes, on a very cold day. And so what happens is, as the water freezes, ice is less dense than water, the ice expands. This pushes outward on the water toward the faucet end of it, creating a large pressure increase, and that can rupture the pipes. And so this freezing and this expansion of ice relative to water can lead indirectly to the bursting of water supply pipes on a cold day. But most materials, as you heat them, they expand, and most materials, as you cool them, they contract. But it isn't always the case, and this is an important example, is water at temperatures near freezing. So here's just a little bit of a summary here. In one dimension, we can deal with thermal expansion in terms of the fractional change in length, which is this linear expansion coefficient times delta T. In two dimensions, we deal with the area, and so the fractional change in area, it turns out, is just 2 alpha, 2 dimensions, so 2 times alpha. And in 3 dimensions, this volume expansion coefficient is roughly 3 times alpha. So when is this useful? Well, sometimes with materials, you'll be given alpha, the equation, the expansion coefficient for length in 1 dimension, but you may not be given it for 2 dimensions or for 3 dimensions. Well, we can just multiply the value in 1 dimension by 2 if we want to calculate the fractional change in area, and we can multiply this alpha by 3 to get a pretty close value to the true volume expansion coefficient in 3 dimensions. But regardless, the fractional change in any dimension is proportional to delta T, and it depends on the material. So that's linear expansion and volume expansion. The last thing we're going to touch upon in these notes are changes in phase. And we're going to go over this more when we get into latent heat, but we're just going to briefly touch upon it a little bit here. So what's going on here when gases change to liquids, or gases change to solids, or solids change to liquids? So when you get to, for example, the boiling point of water, which is at sea level 100 degrees Celsius, you get evaporation, right? The water vaporizes and becomes a gas. What's really going on at that temperature is that there's an equilibrium, in which case there's an equal number of molecules going from the liquid phase to the gas phase, is from the gas phase to the liquid phase. Now this equilibrium depends on the vapor pressure, but you get molecules going in both phases. And similarly, when you're going from solids to liquids at equilibrium, or at the freezing point, you have equal amounts of solids going to the liquid phase as you do going back from liquid to solid. And so for equilibrium conditions, the same number of molecules are going in each direction from each phase. So what's going on here? When you apply heat to a substance, so for example, this is temperature and this is time, and suppose we apply heat. And suppose the object starts at negative 20 degrees Celsius. All of this heat goes into warming the water. And so until you get to 0 degrees Celsius, all of the heat goes into raising the temperature of the water. Now at 0 degrees, you get a phase change. In other words, at 0 degrees, the water molecules have enough energy to escape some of them from the solid phase to the liquid phase. But it takes a lot of energy, because if you look here, as we keep applying more and more heat to the water, the temperature isn't rising. Okay, so where's all the energy going? Well, all of this energy is going into changing the phase of the solid to a liquid, to breaking these bonds or relaxing these bonds, and so now you get a liquid. And so the temperature is not going to go up until you've completely converted it from ice at 0 degrees Celsius to liquid. And so when you have a mixture of liquid and ice at 0 degrees C, it's going to stay at 0 degrees C until it's all ice, until it's all liquid. And that takes a lot of energy. Okay? So all of this energy is going into changing the phase of the water from solid to liquid. And we can reverse the process and go backwards, going right to left. And in other words, if you start off as a liquid and you lose energy, say by putting it in the freezer, this will stay at 0 degrees Celsius until all of the liquid has become a solid, ice, and then it will lower below 0. So there's a lot of energy that goes into changing the phase of the substance, and that energy is called latent energy. Now, once you've liquefied all of the water, you keep increasing, you keep adding heat, the temperature will continue to increase until you get to about 100 degrees Celsius, at least at sea level, and then all of the energy here will go into vaporizing the liquid or changing the phase from a solid to a gas. Okay. And this takes a lot of energy, and so the temperature of the gas will not rise. The temperature will not rise to above 100 degrees until all of the water becomes a gas. And then at that point, if you continue to apply heat, it will go up further. So where does this energy go? Well, if you've ever got a steam burn, it goes into burning your skin, right? Because when this hot steam at 100 degrees Celsius touches your skin is cooler, the steam is going to condense and form liquid water vapor, and therefore we're going backwards here, we're going right to left on the curve, and all of that energy here, that latent heat that was used to vaporize the water, is given back to you in the form of a nice steam burn. And so these changes in phase are associated with the addition or subtraction of a lot of water to and from the gas. Or, I mean, a lot of energy to and from the substance, I'm sorry. There's these curves called phase diagrams, which describe how the phases change with temperature and pressure. We may come back to these at some point in the course, but I'm going to skip them temporarily right now so we can move on to the next subject. So right now, read this section in the book. I think it's section 17.6. We'll come back to it. I think there's a short homework problem on it, but I'd rather focus on some other topics right now and possibly come back to the phase diagrams. So that completes this set of notes here. Okay, now we're going to move on to our next set of notes, which is still chapter 18, and we're going to talk about ideal gases and processes associated with ideal gas. And so these set of notes we'll finish up tomorrow. We're going to get started on them today, and then we'll finish them up tomorrow, and that will be the end of chapter 18. So we're going to start off with the ideal gas law. Some of you might have seen this, and then we're going to discuss processes associated with ideal gases. Okay. And as always, I've included your learning objectives. After completing the notes and reading the chapter, here is what you should be able to do. So in the chapter, we're going to relate some of the microscopic properties of matter. We're primarily going to be dealing with gases to properties that we can measure: temperature, pressure, macroscopic variables. And just as a quick review before we get into gases, the main difference between solids and liquids and gases it all comes back to the attractive forces between the molecules or between the atoms in the substance. And for solids, the forces are very strong and the molecules are very tightly bound to one another. and they're very compressed. And so the molecules and the atoms they're very rigid. They can vibrate a little bit, but they really can't move around much. And you can't compress a solid. When you get to liquids, you add energy to the solid. Substances that exist as liquids, the bonds between the molecules are still there. They're still bound, but they're weaker than they are for solids, and therefore the molecules are free to move around a little more relative to one another because of these weaker intermolecular forces, and that allows liquids to flow. The molecules can move past one another. Gases, you add more energy and you completely break the bonds. Well, almost. For an ideal gas, you completely break the bonds. And so we can think of gases, at least under low enough pressure that we call ideal gases. The density is low enough that these molecules or these atoms are essentially independent of one another, and they basically move around like ping pong balls bouncing around in a container, and the interactions are only very small. So they smash into each other once in a while, then they go their own way, then they smash into the walls of the container, and we can neglect the forces, the binding forces between the molecules. So we're going to deal with gases for now, and we're going to primarily deal with an ideal gas law. And when we say an ideal gas, what we mean, it's right here, is that the density of the gas is low enough and the molecules are far enough apart that they don't really interact except when they collide. And so they're basically just a bunch of balls bouncing around the container with very little interaction between them. And if there's very little interaction and the gases are very light, so the gravitational potential energy is small, these molecules, basically for an ideal gas, all of their energy is kinetic energy. There's no potential energy. And so the faster the molecules are moving at higher temperatures, they have more kinetic energy. For gases, there's typically a certain set of variables that we can use to describe what's called the state of the gas, and we call these state variables. We'll get a little more into what a state variable is later, but these variables define the gas in a given state. So the volume of the container that the gas takes up, or the pressure, which basically is due to the collisions of the gases, of the molecules smashing into the walls. They create a pressure, a force, and absolute temperature. So these three variables, along with either the number of molecules or the number of moles, are what are called state variables, and they define the state of the gas. And there's a law called the ideal gas law, which is derived from given conditions. Okay, so what was found experimentally is that if we increase the temperature of a gas and we hold its volume fixed, so in other words, you have a fixed gas can, for example, at higher temperatures, the pressure of the gas will increase. Okay, and this is one reason why you don't want to put a gas can in the back in your trunk on a hot day. The pressure increases. We'll get to this video in a minute. Experimentally, it also has been determined that if you keep the temperature fixed of a gas, that the pressure is inversely proportional to the volume. And so what that means is that if the gas expands to fill a larger volume, the pressure exerted by the gas is smaller. And that's just because if you have the same number of molecules, but they're spread over a larger volume, they're not going to collide as often with the walls of the container, and they're going to exert a smaller pressure. And so as gases expand, the pressure increases if we keep the temperature constant. Okay. The pressure also, if we keep both the volume constant and the temperature, the pressure depends on the number of molecules in the gas, or the number of moles n, little n. And all that's saying is as we pump more gas molecules into the container, there's going to be more collisions with the walls of the container, and they're going to exert a greater pressure. And when we combine all of these experimentally determined relationships, we get what's called the ideal gas law. And what that says is PV is nRT, or PIV nert. You've probably seen this in a chemistry class. So the product of pressure times volume is equal to the number of moles times a constant, R, the ideal gas constant, times temperature. And we can divide both sides by V, and we get that the pressure depends on the density, the number of moles per volume, times the temperature times the constant. And this is what's called the ideal gas law. And we're going to be using it a lot in the next few days. So to use this law, you have to remember to put the variables in SI units. So that means pressure has to be in pascals, volume has to be in meters cubed, little n is the number of moles, and T has to be in Kelvin, not Celsius or Fahrenheit. This R here has units of joules per mole per Kelvin. So you might say, well, where does joules come from? Okay, well, the product of pressure times volume has units of energy or work, joules, okay? And you can see that pressure has units of newtons per meter square. And if you multiply that by units of meters cubed, the product of P times V has units of newtons times meters, which is force times distance, which is work, which is energy. And so PV, the product, has units of joules. If you want to deal with it in terms of molecules, so chemists like to talk in terms of moles, physicists often like to talk in terms of number of molecules. We can use the fact that if little n is the number of moles and each mole has Avogadro's number of molecules, then n moles must have n times a molecules. So for example, if you have 2 moles of a gas, little n is 2, the number of molecules is 2 times Avogadro's number, or 12.044 times 10 to the 23. And so if we plug this relationship in for little n, so the number of moles is the number of molecules over Avogadro's number, we get this form of the ideal gas law. And then if we combine this R, the ideal gas constant, with Avogadro's number, this becomes a different constant. It has units of joules per Kelvin, and this is called Boltzmann's constant, after Ludwig Boltzmann. And so we denote this constant as KB, Boltzmann constant, and it's 1.38 times 10 to the negative 23 joules per Kelvin. And if we do this, we can express the ideal gas law, PV, instead of in terms of moles, we can express it in terms of number of molecules. So which form that we use depends on whether we're given information in terms of moles or number of molecules. So let's look at this YouTube video. This is a pretty good example, or a pretty good introduction to the ideal gas law. It's about 9 minutes.
Good grammar and spelling are important, but if you want to write essays that inspire...
Hi, it's Mr. Anderson. This is Chemistry Essentials video 14. It's on gases. When you see a hot air balloon flying, it looks pretty stationary, but if you were to look at the molecules inside it, if we were to look at the heat inside it, we'd see there's going to be way more hot air at the top than at the bottom. It's less dense, and that's why the thing is going to float. So when we're looking at gases, basically a real gas is going to be made up of all these independent particles that are all just shooting around, moving around really, really quickly. They're not connected together at all. And so in science, what we can do is we can model that using what's called an ideal gas. And lots of times we'll use the ideal gas law. And this one, PV equals nRT, is one that you should learn right away and learn how to apply it over and over and over again. It's basically built on two things: the kinetic molecular theory, this idea that molecules are bouncing around and they have a huge amount of energy as we increase the temperature, and then the Maxwell-Boltzmann distribution, which means that even though they might collide every once in a while, the energy that they have is going to remain the same and their state is going to remain the same. We can use the ideal gas law to figure out absolute zero, but there are going to be some deviations. In other words, times where this model just doesn't work, and we have to start looking at real gases. And this usually occurs as we get around condensation, that point at which that gas turns back into a liquid again. And so this is going to be a real gas. Air, what's between me and the camera right now, is going to be a real gas. And an ideal gas is built on these two theories. First one is kinetic molecular theory. It's that all of the molecules are bouncing around, moving off of each other, and as we increase temperature, we're going to increase the molecular speed of those molecules. And so that's a gas. Remember, they're not connected together at all. They're just moving around randomly. And then we have the Maxwell-Boltzmann distribution. That means that even though they might bounce into each other, they're not interacting with each other. They're all going to be independent. And so this graph, what we're looking at are a bunch of noble gases, and we're looking at their speed and the probability of having found molecules at that specific speed. And what we'll find is that real light noble gases like helium are going to have a higher speed than those, for example, like argon. We're going to have a lower speed, but they're all independent of one another. And so when we're looking at an ideal gas, we basically have these 5 properties: volume, temperature, pressure, N, which is the number of moles, and then some kind of a gas constant. So you're going to have to look at your units to figure out what gas constant to use. But if we use this model, which we use it 3 times, V is going to be the volume. So let's say these are a bunch of gas molecules. Volume is going to be the size of the container that they're in. T is going to be the temperature, how warm or cold it is, and that, remember, is tied to the molecular motion. Pressure is going to be how much it's pushing out, and if you push in on a balloon, you can start to feel that pressure pushing out on you. And then N is going to be the number of moles, how much stuff is going to be found inside it. And so if we rearrange this, PV equals nRT. That's the relationship. Now you could learn all the different gas laws, but it's better to just learn the ideal gas law and then apply it in different situations. And so we're going to use this simulation at PHET, and we're going to look at Boyle's law. And so that's the relationship between pressure and volume. And so we're going to keep all those other constant, N, R, and T are all going to remain constant. And what we're going to look at is how are volume and pressure related. So I'm going to keep the temperature constant. And if we look at the pressure, it's around 0.69 atmospheres. Now let me decrease the volume. So I'm making the volume get smaller. And so what's going to happen to the pressure? Well, we have to wait for a little bit. We have to wait for that temperature to go back down to 300 Kelvin again. But once it gets to Kelvin, now look, it was 0.69 atmospheres before, and now it's 1.73. And so as we decrease the volume, pressure went up. Now let's increase the volume. So we're making the volume go up, and then let's look at what's going to happen to the pressure. And so we got to wait for that temperature to come back to 300 Kelvin again. And so now we're going to see that the pressure has decreased. So by increasing the volume, we decrease the pressure. And so there's going to be an inverse relationship between pressure and volume. And you could actually apply this in a problem. Let's say we had a balloon at 1.3 atmospheres. That's going to be the pressure. It has a volume of 3.2 liters. What will the volume be if the pressure is decreased to 0.62 atmospheres and the temperature remains the same? Well, we just have a before and after. So we have our pressure volume before, initial, and after. So we'd put in our values before, our after, and then we're going to solve for this final volume. And so we can make sure our units are correct. And so what's going to happen to the volume? The volume is going to increase as the pressure decreases as long as we keep the temperature the same. And a weather balloon, as you send a weather balloon up, the weather balloon is going to get bigger and bigger and bigger. There may be changes in temperature, but it's related to that relationship. Now let's look at what's called Charles' law. We're just going to look at volume and temperature and what happens to the volume as the temperature changes. Let's use this simulation again. We're going to try to keep the pressure constant and the same number of moles inside there as well. And so now we're going to increase temperature. So we're adding heat, and watch what happens to the volume. As we increased the temperature, the volume got bigger, as long as we kept the pressure the same. Why is that? As we're increasing temperature, there's more kinetic movement. Now let's lower the temperature. As we decrease the temperature, those molecules aren't moving as quickly, and what happens? Not pushing out as much, and so the volume's going to go down. So if we increase temperature, volume goes up. If we decrease temperature, volume's going to go down. And so there is a direct relationship between the two. And so hopefully you're learning how to apply ideal gas law. If they're both on the same side, we had an inverse relationship, but now since they're on opposite sides of the equal sign, it's going to be a direct relationship. What's an application of this? Well, you could find absolute zero in a basic chemistry class. And so what we could do is take a balloon and we could measure the volume of the balloon when the gas is around freezing. And so let's say we do that by measuring the circumference around the balloon and then using a little geometry to figure out its volume. If we increase the temperature, so let's say we bring it inside and we really increase the temperature, the volume's going to increase. And if we really lower the temperature, put it in a freezer, then we're going to decrease the temperature. And what you'll find is a linear relationship. And so you could extrapolate that line and we could get to negative 273, which is going to be absolute zero. That's when there's no molecular motion and everything's kind of come to a stop. Now let's look at Avogadro's law. Now we're looking at volume and N. N, remember, is going to be the number of moles of the gas that we put in. So let's look at this simulation right here. Well, there's no temperature and no pressure inside the container, and that's because there's no gas. And so let me squirt a little bit of gas inside there. As we increase that, now those molecules are going to start bouncing around, and so we have a specific volume. What do you think is going to happen as I increase the number of molecules inside there, the number of moles inside there? Well, we're going to try to keep the pressure constant, try to keep the temperature constant, and what's going to happen is, look, the more molecules we put in there, now we're increasing that. We're really increasing the volume. And so we've got a direct relationship. More moles, more volume. And so this is for an ideal gas. Remember, PV equals nRT only works if we have an ideal gas. What is an ideal gas? It's a gas where these things are randomly moving around, and there also is no attraction between those. Those molecules aren't pulling on each other. If they start to pull on each other, then this is going to fall apart. And also an ideal gas only works when we have an infinite number of an infinite volume, which we're not always going to have. But let's say we do have an ideal gas. If I just solve for N, this should always be equal to 1. In other words, PV over RT should always be equal to 1 for any kind of a gas. And so let me just plot that for a specific gas. Let's say we're looking at nitrogen right here. Its ideal gas at different pressures should stay exactly at 1.0. But let me throw up some data.
Okay, we're going to stop here. So let's finish up here with a couple examples. So suppose you have a tire, a car tire, and your volume is approximately constant. And let's deal with the ideal gas law here. So you have a constant volume and you have a constant N in here. So in other words, your tire is sealed. Okay? What's going to happen to your tire pressure as you go from summer toward winter? So the temperature decreases, the amount of air is fixed, the volume is fixed, your car tire. Since T decreases and everything else is constant, if V and N are constant, the pressure is going to decrease when temperature decreases, and the pressure is going to increase when the temperature increases. And so if you never added air or took air out of your car tire, as you went from season to season, you would have, and you kept checking your pressure, which of course lets a little bit of air out just by checking, you would see that your tire pressure in your car tire increases in the summer, and your tire pressure in your car decreases in winter. So let's suppose that T is decreasing and this leads to an increase in pressure, or decrease in pressure. How do we increase the pressure? Well, we have to pump more air into the tire, so we have to increase N to make up for the decrease in temperature and get the same pressure. So in other words, if you think of it at the molecular level, as you get colder, you go from summer to winter, the molecules are at a lower temperature, so they're not smashing as hard into the walls of the tire. They're not exerting as great of a pressure. So we have to pump more molecules in there, more air, to get the same pressure as we had in the summer. And so we need to add air to a tire when it gets colder. And when it gets warmer, sometimes we need to let air out of the tire to keep the pressure the same. And so in mathematical form, we can see that, where is it? The pressure is proportional to the temperature, and the pressure is proportional to the number of molecules. So we're going to be relating states, and so in this case, since PV is equal to nRT, if we divide both sides of the ideal gas law by N and T, we get PV is equal to N times T, and that's equal to R. PV over NT is equal to R. Well, R is a constant, which means even as all these variables change, the quotient of pressure times volume over temperature times the number of moles is always the same. And so if we have an initial state, the initial pressure times the initial volume divided by the initial number of moles times the initial temperature must be equal to the same as the final. Or if we're dealing with molecules, you'd replace little n by big N. And so if we know all of the variables but one, we can solve for the unknown. So let's, as a last example here, before we do example 1, let's suppose that the number of moles is constant and the volume is constant. Then that's the same on both sides, and what that says is that P over T is constant, which means greater pressure equals greater temperature, smaller pressure must be smaller temperature. So let's look at one example of this. So here's the relation right here. P final over T final is equal to P initial over T initial. Here we go.
Can you get those documents on my desk by 4?
I'll get them there by 3:30.
Great.
I've never...
So what happened here? Should actually try this at home. I did it, but this camera, I couldn't catch it, so I ended up going to the YouTube one. So what happens is you add a little bit of water to the bottom of a can, and the water exists in a liquid form. Okay, now if you put this can on your stove, what's going to happen is that you are increasing the temperature of the liquid. And as you increase the temperature enough, then you start to get some evaporation where the liquid evaporates and it forms a vapor, part of the can that doesn't contain anything. So basically what happens is the water vapor kicks the air out of the can. And so you've replaced this volume of dry air above the liquid with this volume of water vapor. Okay? So now if you take this can and you quickly flip it, of course using a glove, of course you're going to burn your hand. You quickly flip it, what's going to happen now? Okay, well now what's happening is the water inside is cooling because you're putting it in the cool water. and the water inside will condense. And that liquid water takes up a lot less space. It's a lot more compact than the water vapor. And so as the water vapor condenses, it creates a vacuum. So no air can get into it. It's submerged in the water, but the liquid water or the gas has been condensed to a water vapor, and so you have a vacuum in this top part of the can. Well, if there's no air in the top part of the can, then that air can't push back against the air outside of the can. So the air outside of the can is pushing inward on the can, and if there's no air to push out, you have a net force from the air outside of the can, which crushes the can. It pushes the can inward, and so you can use air pressure to crush a can. So this is actually a good experiment to try as long as you use gloves, and don't blame me if you burn your hand, because I told you to wear gloves. But it's pretty cool, and it's something you can do at home to see the effect of pressure and how the pressure decreases as the temperature decreases. So we're going to end for today here. Tomorrow's set of notes, we're going to look at special cases of the ideal gas law and get into ideal gas processes, and that'll finish up chapter 18. So have a good night.